Hello and welcome to Solutions Video 3, Solution Features, Solutions Video 3, Solution Features, and Solution Behavior. So, generally speaking, if something's soluble, it can be dissolved. That's what that term means. Sugar is soluble in water. A solution, or a true solution, is a homogeneous mixture of two or more substances in a single phase. And that single phase simply means that if it's a liquid, it's only the liquid is visible. There's no solid particles, there's no bubbles of any kind. Dissolved particles are very small. They can be ions, they can be small molecules. Dissolved does not mean ionized. We need to separate those terms in our minds, okay? We will get to what those things mean, or what the difference is soon. Solutions may exist as solids, liquids, or gas in either form, okay? As I said, a true solution is a homogeneous mixture in one phase with two parts, a solute and a solvent. The solute is being dissolved. It's in the smallest amount. It's usually a solid. It can be a liquid or a gas. The dissolving medium is a substance in largest amount, usually a liquid. Water is often referred to as the universal solvent. And so here we have sodium chloride and water forming a solution of sodium chloride. Now, when you had this solution in your hand in a beaker, you would only see what would look like water. But because you placed sodium chloride in it, stirred and watched it dissolve, and then you can't see it ionized, but you can gain evidence of its ionization by checking conductivity, you have a solution. These are different solutions. Just to point out, we pretty much have every permutation represented here, okay? Um, Pointing one out, gases in a liquid, does not mean bubbles, okay? When you have bubbles in a liquid, that's two different phases. This means oxygen dissolved in water. Think of an ocean, okay? Think of a lake where fish have gills, breathing the oxygen dissolved in the water naturally. And of course, blood. Blood has oxygen both free as O2 in the blood dissolved, and also bound to large protein complexes of hemoglobin. Other neat factoids on here, but generally what you need to see is that pretty much every possible thing you can think of forms a solution. True solutions are homogeneous with particle sizes less than 1 nanometer. They cannot be separated by filtration. They are stable. They don't settle out. And a good example is sugar water. Colloids are larger particles from 1 to 100 nanometers. They are heterogeneous in mixtures. You can see that there is more than one substance present. There's a solid phase, but they're very small, so small that they do not fall out of solution. They are intermediate in size, as I said, 1 to 100 nanometers. They can be solid, liquid, or gas mixed with any other phase. The particles stay in the solution suspended because they have charge differentials that repel one another and keep them in the solution as opposed to falling out. The particles only settle out if something were to neutralize the charge between the particles, and the particles then would attract one another and become too heavy and fall out of the solution. Colloids also exhibit what's called the Tyndall effect, and you have my very cruddy drawing of the Tyndall effect here, but I'll explain, I promise. It's basically light scattering when you put light through the solution. If you've ever been driving in fog, your headlights up in the fog will light the fog up and it's impossible to see. Well, if you take a laser and you put it up to a solution that's colloidal, a great one is Jello, it's easy to get, and you shine that laser through the Jello, it lights up the whole solution like a light bulb almost. And most importantly, it does not allow that laser light to transmit the laser straight through. Okay. Other examples of Tyndall effect, of colloids that can exhibit Tyndall effect are fog, milk, glue, blood, paint, smoke, foam, etc., etc., etc. The Tyndall effect is not just common to colloids; it's also common to suspensions when they're agitated. We'll get to that on the next slide. Colloids also, particles in colloids, exhibit strange movement when they're viewed under a microscope. They appear to be alive and moving. This doesn't mean only living things, but when you look at a peripheral smear of human blood, you can see particles moving, and not just the cells, things like platelets and other small particles that clearly aren't alive or move around. And this is called Brownian motion. This is just the charge differentials between water particles and the other substances in the water basically have like a current, and things move around at microscopic levels. So that's called Brownian motion. Suspensions are particles that contain particles larger than 100 nanometers, and most importantly, they settle out over time. They do not stay suspended like a colloid, and they're heterogeneous, though, like a colloid. So when they're suspended, in other words, if you agitate a suspension, the particles will reflect light and exhibit the Tyndall effect, but shortly thereafter, the particles will fall out of the solution. You can separate a suspension by filtration, okay? You can also separate a colloid by filtration. Should have said that there. So I try to, if you look at the three slides, the particle comparisons, very small particles in a true solution, larger particles in a colloidal suspension, and then, colloidal solution, and then very large particles in a suspension. So this is just an example of a solution. This is hydrochloric acid dissolved in water. It could have gotten there by hydrogen chloride gas being pumped in through a tube, or aqueous hydrochloric acid could have been dumped in. Either way, the solute is the hydrochloric acid and the solvent is water. Solvation is a solute dissolving into a solvent until the solute is stable. When water is the solvent, we call this hydration, but for the purpose of this, we'll call it solvation. Another term, dissolution, is similar, but it refers to the rate at which something dissolves. So solvation is more of the term we're working on this unit. This is a crystal of sodium chloride or some ionic salt being hydrated or solvated by water molecules. Since it's water molecules, we should call it hydration, right? This is just a reaction describing the diagram. So intermolecular forces exist between particles in a solute. Okay, think about that. Your water molecules, for example, have strong hydrogen bonds between. Intermolecular forces also exist between the particles in the solvent. And the solute, pardon me, is going to be, if it's an ionic compound, ion-ion bonds. If it's a covalent compound, then it would be dipole bonds. Or maybe if it's nonpolar, LDFs. But nevertheless, they also exist between particles of the solvent. That would be hydrogen bonds and water. In addition to that, the solute-solvent particles have an attraction for each other. So there's three different types of attraction there: solute-solute, solvent-solvent, and then solute-solvent. This is an important stage of events here, so pay close attention and star this in your notes. When a solute is placed in a solvent, solvent particles completely surround the surface of the solute. And here's the big deal. This is where solubility comes in. If the solute-solvent attraction, that's the new attraction from dropping the salt into water, if it's a salt, is greater than the solute-solute and the solvent-solvent attraction, this is what happens. This is solvation. The solvent particles will separate the particles from one another and pull the solute particles away from the solid and surround them. That's your solvation, forming a solvated solute. The solvation shell is formed. This continues until the solute has reached saturation, which means that water can't dissolve and water can't pull apart any more particles. At this point, an equilibrium condition exists, and all equilibrium means, and this even applies into AP Chem, is that you have an equal forward and backward reaction. So that means at equilibrium we have equal crystallization of particles and then recrystallization of particles and solvation of particles at the same rate. So at equilibrium, things don't stop. Things keep moving. It's just that you're forming product and reactant at the same time, at the same rate. This is a neat graphic of solvation, and I think we just need to play it and watch it happen. And if you're watching closely, you'll see that the different sized ions are being taken by different parts of water. So if we look at the larger green, these would be the anions because they're larger, right? Are being pulled away by the hydrogen ions. And if we look at the other end of it, the smaller ions must be the cations, because cations are smaller than anions, are being pulled away by the negative part of water, the oxygen. And so here is a solution, what it would look like. If you have a solution with no excess ions, this is what it looks like. There's no, if it was oversaturated, particle would be falling from top to bottom. But what we see is a true solution where the ions are all hydrated, and we have free water molecules also floating about. Recall that aqueous solutions containing electrolytes conduct an electric current. This is a feature that helps us to identify solutions. If we had two unknown solutions, there are many tests we would run to determine the properties of the solution, one of which would be conductivity. Remember, dissolved ionic compounds are electrolytes. Ionic compounds not soluble in water will act as electrolytes only when they're molten. So an ionic compound that we would find insoluble on our solubility table could only conduct electricity when it's molten, okay? Substances that ionize completely in water are called strong electrolytes. That means that when you put it in water, all of it forms ions. Ionic salts that are soluble, strong acids, strong bases are strong electrolytes. Now, if you have an ionic salt that's weakly soluble, it's still going to be a strong electrolyte because what does dissolve will form ions. Substances that ionize partially in water are considered weak electrolytes. This is where we need to distinguish dissolving from ionization, okay? Something that dissolves in water, if it's an ionic compound, it's going to form ions. If it's a strong acid, it's going to form ions. If it's a strong base, it's going to form ions. We'll define strong acids, strong bases in a future unit, but these are terms you need to understand right now. Strong electrolytes put a lot of ions in solution. Weak electrolytes only put a little bit of ions in solution. Weak acids and weak bases, which we'll define in the near future, are considered weak electrolytes because they put a small amount of ions in the solution. So types of solutes in water, this is just kind of a recap. Ionic compounds dissolve in water and conduct electricity. I have very polar here because we need to describe the relationship between the particles in the solution. There's lots of charge, okay? Covalent compounds that are polar will usually dissolve in water and they will not conduct electricity well. Nonpolar, of course, won't dissolve, and if it doesn't dissolve, it's not going to conduct electricity, so that's that. Word about miscibility. When two liquids are able to be dissolved into one another, they're called miscible. Factoid about water and isopropyl alcohol. If you take 100% isopropyl alcohol and mix it with water, volume for volume, say 500 mils of each, and put them in the same container, you will not end up with 1,000 milliliters. You'll end up with about 800 milliliters. Really interesting, though. And the fact is that the water molecules and the isopropyl alcohol molecules are able to stack in a way that takes up less space than either of these pure solutions. So it's pretty interesting. Of course, if liquids don't mix well together, they're immiscible. This is oil and water, and you have a nice line showing you the distance, or the less dense oil riding on top of water. This does not conclude video 3. We'll move on to solution behavior real quick. We need to talk about solubility factors. First, if a solute will dissolve depends on temperature. Generally, as you increase temperature, temperature of a solution, the solubility of the solid will increase. The example would be more sugar dissolves in hot tea than iced tea. There are exceptions for that, but that's more of an AP Chem topic. Gases are the opposite. As temperature increases, gas solubility decreases. Okay, so gases prefer to be in a solution with less energy, and that makes sense because if you make the particles move faster, they're more likely to be able to escape the solution. And there's your example there, hot Coca-Cola escaping the solution. The nature of the solubility is a huge factor. If they share the same polarity, if they're both relatively polar, they will dissolve well in one another. If you have a nonpolar solute going into a polar solvent, that's not going to dissolve. So like dissolves like is the general way we think about this. Polar solvents dissolve polar solutes. Nonpolar solvents dissolve nonpolar solutes. Like dissolve like gets said a lot. It's an overgeneralization, but it works for what we need to know. So here's some examples. Benzene does not dissolve in water, but it does dissolve in CCl4, carbon tetrachloride. Glucose does not dissolve in benzene, but it does dissolve in milk. Water does not dissolve in carbon tetrachloride, but it does dissolve in milk. So using the above information about what we know, we need to indicate whether these things are polar or nonpolar, and it should be pretty quick and easy. We already know about water, don't we? We know that water is a polar molecule, so let's go ahead and put a P there, and we can use that as our Rosetta. So water does dissolve in milk, so milk must be then polar. Does not dissolve in carbon tetrachloride, so that's got to be nonpolar. Benzene does not dissolve in water, does dissolve in CCl4, so that's got to be nonpolar. Glucose does not dissolve in benzene, but it does dissolve in water, polar. So this is just a quick little question analysis set to determine polarity. Just by examining substance's ability to dissolve gives us an idea of its properties. Solubility. Pressure is a big factor for solubility of gases. If you increase pressure in a system, you increase the solubility of the gas of the liquid. So if you increase the pressure out here in the air, the gas particles are more able to go into solution. Does not apply. So if you change the pressure, it's not going to change the solubility of a solute that's solid, only gas. Okay, very important to make that distinction. Solubility rate. Assuming if something can dissolve, how do we improve the speed with which it dissolves? Number one, again, is increasing temperature. The more kinetic energy, generally speaking, the more collisions you have, the more likely your solute will dissolve faster. There are exceptions to this. Agitation will always help. The more contact with the surface of the solute and the solute will dissolve faster. Agitation helps a great deal. Finally, solute surface area. The smaller particles you have give a greater surface area for the solvent to work, and therefore increasing surface area or making particles smaller will increase the rate of solubility of a solid. This concludes video 3. You should have taken high quality notes. This is not video 4. Make sure you rewatch portions of this video as needed and come to class with questions.